This PPT is visible to you?
Yes, sir.
Okay.
Sir,
Yes, it is visible.
Okay, in the previous class, we have discussed about divide and conquer approach. Now we will discuss about different examples in divide and conquer approach. We have already discussed your binary search algorithm. In binary search algorithm, we divide the problem into small subproblems until the problems becomes very minimal. After that, we have solved all the subproblems, and then we combine the different solutions to make a complete solution. Now, the another one is another approach is your merge sort. Okay, merge sort, it is a sorting algorithm. Sorting, one more strand. Okay, in which you arrange the elements either in ascending order or in descending order. This algorithm also follow the divide and conquer approach. So merge sort is a very popular sorting algorithm that uses the divide and conquer approach to sort any given array or your linked list. It may be your characters or strings also. So there are some reasons to learn the merge sort algorithm. Actually, it uses your divide and conquer approach. So in merge sort algorithm, it is one of the fastest sorting algorithms that works in order of n log n time. The time complexity of this algorithm is your n into log n. It is also the best algorithm for linked list also. In linked list, it also takes n log n time, either in your best case, worst case, or in your average case. So merge sort always performs best in all the cases. So it is an excellent algorithm for learning your recursive problems, to learn about recursion and problem solving, in which we use the divide and conquer approach. All the problems which are solved in divide and conquer approach in all the sorting algorithms, merge sort performs well among all the algorithms. So it is the best algorithm for analysis of the recursion. This process of the merge sort is an excellent idea to learn the two-pointer approach, in which both pointer will move in the same direction to build the partial solution. So this approach can be used to solve several coding questions, the divide and conquer approach. In this approach, we have divided the problem in small subproblems. That part is called your divide part. In the divide part, we have divided the problem into two equal subproblems. In the divide part, the next part was the conquer part. In the conquer part, we have solved all the subproblems recursively. In first part, divide part, we have divided the problem into two equal subproblems. And in conquer part, you have solved both the subproblems recursively. And the last part is your combined part. In the combined part, you have merged both sorted parts, both the sorted subproblems into a larger sorted array, into a larger sorted problem. So there are three parts. So you discuss that. In divide part, we divide the sorting algorithms of size n into just two equal halves, just two equal subproblems of size n by 2, by calculating the mid value of the array. On the basis of your middle value, we have divided the sorting problem of size n into two equal subproblems of size n by 2 on the basis of your middle index, your mid value. Now there will be two problems, two subproblems. One will be your sorting subarray with size 1 to mid, and subproblem second will be your sorting subarray with the size mid plus 1 to the maximum size. Next is your conquer part. In the conquer part, we have solved each subproblems recursively. You can also say that we sort both similar subarrays using recursion by calling itself one again and again. We sort the smaller subarrays using recursion. During this process, we don't think about the solution of the problem, because recursion will already do it. And in the combined step of the merge sort, we have merged both sorted subarrays to get the final sorted array. It means we have combined the solution of both n by 2 size subproblems to solve a sorting problem of size n. This is the basic concept of your merge sort. Let us see with an example. Is it visible?
No.
No, sir.
Not yet.
Now it is visible. Okay.
Yes, it is visible.
Okay. Suppose this is an array of size 4, in which you can see that there are 4 elements, 38, 23, 27, 48, and 10. There are 4 elements in the array. And you have to sort this array using your merge sort. In the first step, you will divide the problems, you will divide that array into equal to halves. You can see in step 1, you can split the array into just equal to halves. The part itself will be in the middle. Okay, there are 2 subarrays, 38 and 27 in first subarray, 43 and 10 in another subarrays. In the first step, you have just split the array into just two equal halves on the basis of your middle index. Okay. In the next step, you have again split the subarray into equal to halves until the problem becomes minimum. Minimum means after that you cannot further divide that problem into again and again. Okay, you have split that subarray into two halves. Now they become the array of unit length. Now you cannot no longer divide an array of unit length. Okay. After that, after dividing the subarray into minimal, you will merge these subarrays after a comparison. You can see that you have merged these two minimum problems, 38 and 27. After comparing each other, 37 is compared with 27. Here 27 is minimal element. And you have solved these. 27 is in the first place and 38 in the second place. After finding out the solution of 38 and 27, you have merged these subproblems in merge sort. Again, the merging process will continue until we will find the total solution, complete solution of the problem. Now you can see here, there are two subarrays now, 27 and 38, 10 and 43. Now we will again merge these two subarrays after finding out the solution. Now 27 will compare with 10. In both elements, 10 is minimum, so 10 will be moved on the first place and 27 will be in the second place. Then 27 is compared with 43. Now you can see that 27 is smaller than 43. So 27 is third place. So sorry, second place, and 41 in the rest place. Now 38 is compared with 10. 38 is greater than 10. Now 38 is compared to 43. The 43 is greater than 38. So 38 will be in the third place and 43 will be in the last place. This is the merging procedure, combining procedure. After finding the solution of each subproblem, we merge these subarrays to find a complete solution of a whole problem. This is the divide and conquer approach, in which you have divided the problem on the basis of your middle element into just equal to halves. You have divided these until the problems become your minimum. Minimum means after that it is not possible to divide that problem. After divide part, you have find out the solution of each subproblem. In every step after finding out the solution of each subproblem, you have merged all the subproblem solutions to find out the complete solution of the particular given problem. This is called your merge sort procedure. So there are 3 steps in merge sort on the basis of your divide and conquer steps. You can also say divide and conquer steps of merge sorts are your divide part, in which we calculate the mid index. The mid was your 1 plus n by 2, first element and last element divided by 2. In the first part, we have calculated the middle index. In the conquer part, we have recursively sort the left part of size n by 2 by calling the same function with mid at the right end. And in the second part, we have also recursively sort the right part of the size n by 2 by calling the same function with mid plus 1 as the left end. So there were 2 parts in conquer first part and conquer second part. And then the last part, combined part, you have used the merge procedure. That is called your merge procedure, function to merge both the sorted halves into a final sorted arrays. So this is the complete merge sort and merge procedure to sort a given array and a given linked list, or you can say any elements, either they be strings, anything. So this is as your merge procedure. Okay. Now I will show you some simulation of merge sort. I'm sharing you a visualization of merge sort. Is it visible to you?
No.
I think now it is visible.
Yes.
Just go through it.
Our task is to sort these balls by brightness. This robot, however, is short-sighted and can only compare balls when they are placed directly in front of its eyes. Bubble sort compares every adjacent pair of balls, moving the brighter ball forward. This brings the brightest ball to the end of the row, where it should be. Another pass is performed on the remaining unsorted balls. And so on. Quicksort starts by randomly picking one ball, called a pivot. It then rearranges the other balls by comparing them with a pivot. Balls brighter than the pivot are moved to the right, and darker ones to the left. The pivot can now be placed where it should be. Our row of balls is now split into two smaller, unsorted rows. Each is sorted in turn using Quicksort. Pick a pivot. Let's assume the left half of our input somehow miraculously gets sorted. And so does the right half. Can we use this to quickly reach a fully sorted list? Note that simply interleaving the two sequences doesn't work. Instead, we'll employ a more clever technique called merging. We compare the first two elements and remove the darker one. We repeat this again and again until one side becomes empty, and then simply remove what remains. This process produces the elements in sorted order. Now our robot will perform this merging algorithm. Being short-sighted, it must bring the objects close to its eyes. When merging is done, the balls are pushed back to the bottom shelf, and the sort is complete. Now let's get back to a random permutation. To perform the merge algorithm, we need the two halves to be sorted. Instead of relying on miracles, we'll sort each half ourselves. We'll do it using merge sort. We'll split each half in half again and again until we reach sequences of size 1. These are already sorted. And now we can work our way back up again until we reach a fully sorted sequence. Two sequences of size 1 can be merged using a single comparison, creating a sorted sequence of size 2. Now that we have 2 of these, we can merge them into a sequence of size 4. And so on.
Okay, in the merge sort, we have seen that we have first divided. After that, we have divided until it becomes your minimum. After that, we have done comparisons with the elements, and we can find out that which element is the minimum that will be in the first position. Every time, I have find out the correct position of every element. So in merge sort, either in your best case, in your worst case, or in average case, every time it performs same in all the cases. In all the cases, it performs same, either in first best case, average case, or your worst case. Now I will show you a pseudo code for this. I think now this is visible.
No, sir.
Okay. Okay, here you can see that first one, we will start from main. Here is the int main. This is a given array with 6 elements. Okay, given array is printed here, and
Sir, please zoom it.
okay, now this is clear.
Yes, sir.
Yes,
Okay.
yes, it is clear.
Here is main function int main. Okay, these are the elements which you want to sort in ascending order. Okay, here this is a function called merge sort. After calling the function, it will jump this function void merge sort. Here you have find out the middle element int mid. It will calculate your middle element. Middle element is calculated on the basis of your first element and last element of the array. That will be divided by 2. This is your middle element, the value of middle element. On the basis of your middle value, the complete array will be divided into just 2 equal halves. First one is your merge sort from 1 to m, element 1 to m. This is the first half of the array, and another half of the array is from m plus 1 to the last element is r. Now you can see that complete array is divided into just 2 equal halves. Merge sort array 1 to m and m plus 1 to r. Now after dividing approach, it will merge the solution of all these subproblems. Now merge procedure will be called. But where is the merge procedure? Merge procedure is on the top of the program. This is your merge procedure. Okay. In the merge procedure, you see that there are two loops for sorting the elements. Here you can say that for I equal to 0 to I less than n I plus plus, I am comparing the elements, copying the data in the array. Now I am comparing the elements, one elements to the other elements. Okay, if L of first array element is less than the second of the element, then I am putting that value in the array. Otherwise, putting the second half value in the array. In the merge procedure of the first half, you can also see that. Otherwise, the element will be remain in the same position. I am doing it until j becomes less than your n by 2. Okay. In merge sort, in the main part, at first I have divided the problem into just two equal halves. In equal halves are done in the merge sort procedure, where there are two subarrays, merge sort array 1 to m and merge sort array 1 m plus 1 to r. After dividing the problems into subproblems, I have called the merge procedure. This is the merge procedure. In the merge procedure, I have compared the values of the given array elements. After comparing, I have found out that which element will be the minimum that will be in the first position. Okay. When I run this program, actually this is compiling. After compilation, you can see the result. Is it clear to you how divide and conquer approach works? How the array is divided in the merge sort, and how the subproblem is calculated in each pass. Actually, it is taking some time. Okay, it is taking some time. So you can see the output of the arrays, given arrays 12, 11, 13, 5, 6, and 7. Then the sorted array will be your 5 to 13. This is the final output of this program. Okay. Then the complexity. The complexity of merge sort will be your n log n. Because merge sort is a recursive algorithm. Every time it calls itself, and the recurrence relation of merge sort will be Tn equal to 2Tn by 2 plus order of n. Every time it will take order of n time to merge the subarrays. To merge the subarrays. Here Tn is the complete time and is complete time to run the algorithm size n, and 2Tn by 2. Here this problem is divided into just two equal halves, that is your n by 2. So to total time equal to your 2Tn by 2. And in the merge procedure, in every step it will take your order of n time in every step. So this is the recurrence relation of your merge sort algorithm. You can solve this recurrence relation using either master theorem or any other method to solve the problem. As we have also discussed that, I am showing you in paint also. Is my paint section is open?
Not yet. Not yet, sir.
I think now it is visible. Is it
Yes,
visible?
it's visible, sir.
Okay.
Yes, sir.
The recurrence relation of the merge sort is your Tn equal to 2t n by 2 plus order of n. Okay. In this recurrence relation, I have divided the problem of size n in just equal to halves. You can see with the help of a tree. The size of the complete problem is your n size. Further, it is divided into just equal to halves, n by 2 and n by 2. And this function is called your recursively. The division will be until the problem becomes your minimal. So further, it is also divided into just two equal halves. And the problem size will be your n by 4, n by 2 square, n by 2 square, that will be your n by 4. N by 4 and n by 4. Again, this function is called your recursively. Further, it will be categorized, it will be divided into two halves. Now the size of the problem will be n divided by 2 to the power 3. That will be your n by 8, n by 8. Here also n by 8 and n by 8. In the same manner, right hand side. This problem is also further divided into of the size of your n by 8, n by 8. This last subproblem will be also divided into just two halves. That will be your n by 8, and that is also your n by 8. This will be divided until it becomes your minimum. What will be the minimum? Minimum will be your n by n, because the value of n by n equal to 1, until it becomes a unit element. It will be divided until. Okay, and every time you can see that just taking order of n time. Order of n time in the merge procedure. Every time it takes n time in conquering the element and merging the element. This problem of size n is divided into just two equal halves n by 2, and it takes your n processing time in each every steps. Here it will take your n time. Here it will also take your n time in both elements. Here it will also take your n time in all the 4 elements. Here it will take also n time in all the 8 elements. Okay. In merge sort, it is a complete binary tree. So the size of this tree will be your log of n. The size of this tree will be your log of n. And every time it is taking your n time. Every time it is taking n time, and the size of the tree, the height of the tree is your log n. So total time will be your n into height of the tree. The height of the tree is your log n. You can see that n is your conquering and combining merging time, and height of the tree is your log n. And take this is in every step, either conquering or combining or merging the solving the in every pass it takes your n time, and height of this tree is your log of n. So the complete time will be your n into log n. So the complexity of merge sort is your n into log of n. And what will be the best case? And what will be the worst case and in average case? In all the cases, best case will be if the elements are already sorted. If the elements are already in a sorted manner, that will be the best case in sorting in any sorting algorithm. Then how much time it will take? In the best case, it will also work same, because every time same problem is divided into just two equal halves. After dividing, it will compare all the elements. In the comparison, it will again take order of n time in every pass or in every steps. So either in the best case or worst case or average case, merge sort works same. So in all the cases, the complexity of this sorting algorithm is your n into log n. Now it is clear to all? I think now it is clear. Is there any questions?
Yes, sir, it's clear.
Okay, good if it is clear. So this is the complexity of your merge sort, time complexity of your merge sort algorithm. So in all the cases, all the three cases, it takes your n into log n time. And space, auxiliary space, it takes your order of n time to save all the elements, because in merge sort all the elements are copied into an auxiliary array. Auxiliary array means you have taken one more array to store these elements. So an auxiliary space is required for merge sort, because after comparison you have find out the minimum element and you have saved that element in the next array. That is your auxiliary space, auxiliary array. So it takes your order of n time in the space complexity. Okay, there are some advantages of your merge sort. The merge sort stability is very high because it is a stable sorting algorithm, which means it maintains the relative order of the equal elements in the input array. If all the elements have the same value, then it will not change the order of these elements. That is called the stability. So merge sort is a stable sorting algorithm because it doesn't change your order of the equal elements in the array. And one more advantage is that its worst case performance is best in all the sorting algorithms. The worst, because worst case time complexity of this algorithm is your n log n. which means it performs best even on the large data set. Quicksort is not good for large data set, but in merge sort it performs too good for large elements, also large data set of the elements. And merge sort is naturally, it is also parallel algorithms, which means it can very easily parallelize to take the advantage of multi-processors or threads. These are some advantages of merge sort. There is only one drawback of the sort, that is the space complexity, because it takes one extra array, one auxiliary array to store all the elements. It requires additional memory to store the merged subarrays. After comparing the elements during the sorting process, it takes your extra space. The space complexity of this algorithm is your order of n. It is also not in place algorithm because it takes extra space. That is called your in place or out place. So it is your out place algorithm because it requires your additional memory to store sorted data. So it is not good in concern of your memory uses, and it is not always very optimal in a small data set. It is very good for large data set, but it's not optimal for a small data set. If you have a very small data set to merge, and merge sort has a high time complexity than other sorting algorithms. For example, if you have already sorted algorithms, you have already a sorted array, and you have a very small data set. At that case, the insertion sort takes your order of n time. Insertion sort take order of n time because the elements are already sorted, and the data set is very small. So in such type of cases, merge sort is not suitable when the data set is very small and the elements are already sorted. So this can result in slow performance for a small data set, but for a large data set, it is best algorithm. Now it is clear?
Yes, sir.
Okay. Now the next algorithm is your quicksort algorithm. One more approach which is used
Sir,
to
we
divide
cannot
and
see the screen.
Okay, I'm sharing. Wait a minute, I'm sharing quicksort. Wait a minute, I'm sharing quicksort algorithm. I think now it is visible. Is it visible?
Yes,
Yes,
it's
sir.
visible.
Okay. Then quicksort. Quicksort algorithm is also follows the divide and conquer approach. This algorithm was developed by Tony Ho, a computer scientist in 1959. For developing this algorithm, he was awarded by the Turing Award, that is also called your Nobel Prize of the Computer Science, after developing this sorting algorithm. This sorting algorithm becomes very popular due to its efficiency and simplicity. nowadays you can say that quicksort is best algorithm. Why quicksort is best algorithm? Why it is called the fastest algorithm? Although we have multi-sorts with the complexity of n log n, still quicksort is called your fastest sorting algorithm. It is also based on the idea of a divide and conquer approach. There are many reasons for this. First one is efficiency. In the best case, quicksort also works like as a merge sort. The best case complexity of the quicksort algorithm is also your n into log n on an average. It is often the best choice for sorting because it operates efficiently and log n average time. In the worst case, it takes n square time. Otherwise, in the average, on an average, it takes your order of n log n time. It also uses the concept of your recursion. The recursive structure follows the recursion. In quicksort algorithm, we partitions the problem. We partition the algorithm into subproblems, subgroups. The partition algorithm using quicksort introduces you to problem solving using same as your merge sort two-pointer approach. It is also your in-place algorithm. It does not take your extra space to store the sorted elements. It is an in-place algorithm, sorting algorithm. So it reduces your memory access compared to the merge sort. In merge sort, that is your outplace algorithm that takes your order of n time extra space, auxiliary space to store the sorted elements. But in the quicksort, it is your in-place sorting algorithm that takes no extra space, no auxiliary space to store the sorted elements and compared to your merge sort. It also uses your randomization. We use a random generator to divide the problem, to divide the main problem. A random generator is used, a randomization is called. So it is an excellent algorithm to the concept of your randomized algorithms. Randomized. So randomization is a tool to improve the efficiency of the real-time systems because we randomly divide the problems. In quicksort algorithm, we take a pivot element to divide the problem, to partition the array. While in case of merge sort, we find out the middle element every time to partition the array. But in quicksort, we partition an unsorted array around some input value. That input value is called your pivot value. That is called your pivot value of the problem. All the values in the left part, that will be the less than to the pivot value, and all the values in the right part are greater than the pivot value. And after the partition, the pivot value will be placed in the correct position. The pivot value will be your last element, first element, middle element. We will randomly select a pivot value. And and on the basis of that pivot value, we partition the algorithm, we partition the problem, we separate the problem into just two halves, not just two halves, on the basis of the pivot elements. and all the values in the left part are less than the pivot value, and all the values in the right part are the greater than the pivot value. After the partition, the pivot value will be placed in the correct position in the sorted array, in the sorted order. Now we have a same situation. The left and right halves are still unsorted. Again, we will select a pivot value and we will fix that pivot value in the subarray. We will partition the complete problem until it becomes your minimum. If we sort both the halves recursively using the same function, the entire array can be sorted. That is very simple. All the values on the left side are less than the pivot, and the pivot is in its correct position, and all the value on the right side are greater than the pivot value. In every pass, the pivot value will be in its correct space. So it is in place algorithm because it doesn't take any extra space, extra array for storing these sorted arrays, because every time in every pass the pivot value will be in its correct position, and all the elements which will be less than your pivot value, that will be in the left side, and all the elements which will be greater than your pivot value, that will always be your right side of that pivot value, and pivot value will be in the its correct position. So in divide part, I am dividing the array into two different halves on the basis of the pivot value. And in the conquer part, I have sorted both the halves recursively by calling again and again the randomized functions. And in the combined part, the entire we will find out the entire array, sorted array. So there is no need of combination of merging the part, because there is no need of any extra space because it is an in place algorithm. So this is a divide and conquer approach of the quicksort algorithm. I'm also sharing one example of quicksort. Is it visible?
Yes, sir.
Quicksort. Okay. Now you can see that algorithm, it is a divide and conquer algorithm. Every time you elements the element that is called your pivot element. Okay. Partition, you arrange the partition on the basis of your pivot value. Now all the value are less than. And right here, same case. Okay. This is the example. Okay. This is the example. Let us take an array of 5 integers. These are your 5 integers: 10, 25, 3, 5, and 0. Okay. These are the elements in the array. The start index is 0. Pivot element index is also 0 in the first case. Ending value is 4. The pivot element is 20 in the first case. In the first pass, the pivot element is the last element. I have decided that the last element is the pivot element. Then I have compared 20 with the 10. Now check that 10 is less than 20. Yes, it is true. Yes, it is true. Now this is true. Then this pointer will be moved to next. Now this pointer p index will be in the next position 25. Now 25 will be compared to 20. Now I will again check 25 is less than 20. No, false. This condition is false. Now I can first pointer I will be moved to 3. I will be in the third position. Now 3 will be compared with pivot value 20. 3 is less than 20. Yes, true. Now P index will be incremented by 1. This is called your double pointer. Okay. Now 3 and 25. This will be interchanged because the value of 3 and 25. Now 10, 3 and 25. Now 25 will be compared with 20. Now again check. This is smaller. Again this will be incremented. Now 50 will be checked with 20. 50 is less than 20. The false condition. Now 25 will be replaced with this position. After that, the pivot value will be at this position and 50 will be here. Okay, I will show you with a visualization of quick sort. Visualization of quick sort. Here is the visualization of quick sort. Now you can see the visualization of quick sort.
In this video,
Is it visible?
Yes, sir.
Yes, sir.
Okay, now you can see the visualization.
quick sort, how it works, and then at the end of the video, we'll go through the Python code together. The first step is to put the indexes onto our array. So here are the indexes. And the second step is to put the start and the end on
You can see that these are the indexes 0, 1, 2, 3 and 4. These are the elements 2, 5, 3, 1 and 4.
to this array. So the start is S and the end is E.
Okay.
The third step is to calculate the mid index. And the formula is S plus E divided by 2. So
Is it-
S is currently at index 0, E is at 4, so we get 4 divided by 2, which gives us 2. So mid is at index 2. And the fourth step is to select our pivot, and that's very easy to do. So wherever our mid index is, we look at the number in the array, and this will be our pivot. The fifth step is to do something called partition, and I like to think of it as a game with 2 players. So we replace S with L and E with R. And the goal of this game is to get all the numbers less than the pivot on the left bubble. So for example, here we have 2 and 1, and all the numbers larger than the pivot to the right bubble, so 5 and 4. Here, the order does not matter as long as you get the numbers in the correct places. So the player L will find us a number that is larger than the pivot or equal to the pivot. Let's see. No? Yes, because 5 is larger than the pivot. Now, R will find us a number that is either smaller than the pivot or equal to the pivot. So note 4 is not smaller or equal to the pivot. So let's take a look at 1. And yes, it is. 1 is smaller than 3. And what to do next? Well, we simply swap 5 and 1. So now you see that 1 is in the left bubble and 5 is in the right bubble. And then we move L to the right and R to the left. And repeat this process. Remember, L will try to find us a number that is larger than the pivot or equal to the pivot. And L already found 3, right? It's equal to the pivot. Now, R will find us a number that is smaller than the pivot or equal to the pivot. So R also finds 3. And we swap 3 with itself. So just swap in place. And then we move L to the right and R to the left. At this point, L and R have crossed each other, and this indicates that the partition game is finished. So notice that all the numbers smaller than 3 are to the left side, and all the numbers greater than 3 are to the right side.
Here you can see that the third position in this example, it have calculated that on the middle element as a pivot element. You can see that third is in its correct position. The elements in the left side are less than the pivot elements, and the elements in the right side are the greater than this its pivot element.
And all the numbers greater than 3 are to the right side.
Okay.
Before we move on to the next step, let's first summarize the partition game. So while L is less than or equal to R, basically this just means repeat these following steps until L and R cross each other. And that's when the game finishes. While the number in the array at L is smaller than the pivot, we move L to the right. So after this while loop, L will find us a number that is
Okay, we
either
will discuss
larger
it.
than the
I will
pivot,
discuss it. Okay,
or
now you see the example.
we just replace L with a different variable called index. And why do we do to replace L? We just replace L with a different variable called index. Partition the array, right? So from the index to the end of the array will be in its own box, like this, and the other side will also be in its own box. Now, quicksort is recursive in nature. So basically, we repeat quicksort on the left side first and then on the right side. So always on the left side, we put S, which is the start, and then E at the end. We calculate the mid. So S is 0, E is 2.
Okay, now further, it is also use quicksort algorithm in the first half and also quicksort algorithm in the second half. Again, the same procedure will be repeated recursively until we get the complete solution of the problem. Okay, now I will discuss with the help of your I'm sharing one more. Is it visible now?
No.
Is it visible on paint page?
Yes.
Okay, okay. In quicksort algorithm, we have divided the array on the basis of your pivot element. The pivot element position will be any place. Okay. Suppose this is an array. In the best case, if the elements are already sorted, or you can say the best case every time in the quicksort case, best case will be if every time the middle element is the pivot element. In the video, he has discussed the best case. A best case of the quicksort algorithm is every time the middle element will be the pivot element of the array. If every time the middle element is the pivot element, then every time this problem will be divided into just two halves. If every time the middle element is the pivot element, then this type of graph will be generated. And in every case, in every step, it is also taking your n time, and the maximum height of the tree will be log n, such as in the merge sort case. It is the best case. If every time the middle element is selected as a pivot element, so every time the partition will be done equally into two halves, then this algorithm also works same as your merge sort. But there is only one difference, that it is your in place algorithm, and merge sort is your out place algorithm. So quick sort will not take your any extra space in the best case. While in the worst case, if every time the last element or the first element is selected as a pivot element, then how the partition will occur? If the last element, every time the last element is a pivot element, or the first element, suppose in the first case, if the first element is the pivot element, then there will be only one element at one side and remaining elements will be in the next side. Only one element is here and minus one element is here. In the next case, in the next call, also one element will be in the left side and remaining and minus two element will be in the right side. Because in this procedure, in this type, in the worst case, the pivot element is the first element. Every time it is dividing the problem into just two halves. One half, in the one half there is only one element, and in the other half there is n minus remaining n minus one element in the worst case. So in every phase you can see that there will be only one element in one side and remaining elements are on the other side. And every time it is taking your n time. In the every step it is taking your, either in partitioning or in sorting, it is taking your n time. In this case, the height of the tree, that will be your n size, because in the left hand side there is only one element, and in the right hand side remaining elements are on the right hand side. So in the worst case, the total complexity of this algorithm will be n into n. So that will be your n square in the worst case complexity of the quicksort algorithm. In the best case, every time the problem is equally divided into two halves, n by 2, n by 2. But in the worst case, either it is in the first position or in the last position, on the basis of your pivot element, the partition is formed. So in the best case, the maximum height of the tree will be your n, and the total complexity of your algorithm will be your order of n square in the worst case complexity in the quicksort algorithm. So the code of, we will discuss the code of this algorithm. I think now it is clear. Sort and quicksort. There is. This is the code of your quicksort algorithm. On the basis of your element, the array is divided. In first, you can see the main. As you have defined the elements, array elements. Okay.
Sir, could you please just zoom it?
Okay. I'm zooming it. Now it is visible.
Yes, sir. It is visible.
This is the program for your quicksort algorithm. In the quicksort algorithm, this is the main function. Inside the main function, you have entered the size of the array, and now these are the elements. Okay. This is your quicksort procedure in the array. After calling this function, we have jumped to the quicksort. In the quicksort, you have checked that the first element is less than, and yes, of course, first element is less than. Now you have calculated the index for partitioning. Partition is first on the basis of first and last element. Now there are partition on the basis of your pivot value, p index. That is your p index on the basis of your pivot value. On the basis of your pivot value, we have divided the complete array into just two array. First one is quicksort array start to pivot value, and after that array pivot value to the end value. In the partition algorithm, based on the your p index, your pivot value index on the pivot, if the value of pivot that is your less than the element in the last, now I will check the pivot value for all the elements. I will compare all the elements with the pivot value. After comparing with the pivot value, I will find out the exact position of the pivot value after swapping that value with the adjacent value. Okay. After this comparison, I have find out the actual value, actual place or actual index of the pivot value. On the basis of this pivot index, I have divided the problem into again two parts. Again, this partition function will be recursively called until it becomes your minimum. Okay. This is the code. We run this code. Here you can see that console, enter the size of array. Suppose the size of the array is 6. We have entered the elements 78, 25, 14, 36, 72, 35, 21. Okay, these are the 6 elements which we have entered in the array. After entering the elements, the partition is performed and the elements of the sorted are these. Okay, so quicksort is a divide and conquer approach algorithm. It is best for a small size of array. It will perform best if the size is small. Okay, stop presenting. Wait a minute. Okay, so we have discussed all the cases in the quicksort algorithm. Okay, quicksort is the algorithm which works on the approach to a divide and conquer approach. So quicksort is also an in-place sorting algorithm because it does not use your extra space in the code. So it is an in-place algorithm. Every recursive program uses call stack in the background. So therefore, the time so space complexity of the quicksort will depend on the size of your recursion call stack, which will be equal to the size of your recursion tree, and that is not your any extra space. So the height of the recursion tree will be depend on your partition process, which I have already discussed there. If the pivot element is the middle element, the height of the tree is your log n. If the pivot element is the middle first element and the last element, the height of the tree is your n. Okay. In the worst case scenario, the partition will be the unbalanced tree, resulting in that only one recursive call in each level of the recursion. In other words, you can say that the generated recursion tree will be skewed in nature, and the height of the recursion tree will be your order of n in the worst case. Okay, in the best case, that is your order of n. Okay, in best case scenario, that is your log n. So the time complexity depends on the height of the tree. Okay, in the best case, the height of the tree is log n, so the time complexity is n log n. And in the worst case, the height of the tree is your n, so the time complexity is your n into n, that is your order of n square. So this is your quick sort algorithm. Okay, I will send all the notes of your divide and conquer approaches in the group. Kindly go through it. Now it is clear to you. There are three approaches in the divide and conquer approach. First one is your binary search, then your merge sort, and your quick sort algorithm. Okay.
Yes, sir.
Okay, I think it is clear, and it is enough for today also. Okay. In the next
Okay.
class, we will discuss about greedy approach.
Okay, thank you, sir.
Okay, thank you,
Okay,
dear. I
sir.
will send all the notes in the group.
Okay, it will be nice if you're sharing those notes.
Okay, okay, I will send it. Okay. Okay, thank you, class.
Thank you, sir.
Okay.
Thank you, sir. Thank you, sir.
Thank you, sir.
درسا تمام شد همکارا. بله. بله. همصنفا کسی میشنوند؟ بله بله
دوستانو استاد پکې نه ښکاري. استاد څنګه درس یې خلاص شو؟
والله زه فکر کوم چې خلاص شوی ده. زه هم یو دوه دقیقه مخکې بیرون ته تللی. همصنفا هستن میشنوند؟ درسا تمام شد؟
با فکرم درسا بخیالم تمام شده. مگم یه چیز است یک خواهش از استاد چیز کنیم که می درسا یه چیزی که یا پخش میکنه یا یه چیز میکنه باید یه چیز هم باشه، مثلا یک چپتر واری باشه و سر پرکتیکل باید بسیار زیاد چیز کنیم. ما کوشش کنیم یه خو یک دقیقه نتش بند میشه، باز دیگه چیز میایه بیخی بر ما خو بیخی عجیب واری معلوم میشه. نمیفهم شما را.
چپترهای از اینا به شکل PDF داده شده برای کلگی، ولی سلاید دارن. تعداد از استادا سلاید دارن و شکل PDF دارن. دوباره اگر اون رو همراه ما شریک بکنه خوب است. درسایی که قبلا داده بود شریک کرده گروپ هست دیگه. درس ها یونیت کتابوار در PDF هم هست، ولی سلاید که جور کردن اونا رو هم شریک میسادن دیگه همراه ما بشن. من یادم درس امروز مقدار شده گروپ شریک شده. در گروپ هستن آقای دلاور صاحب شما؟
بله ها در گروپ هستم بیاده. ما این چیز است گفتم نیتی بسیار مشکل داره. بعضی وقت بند میشه، بعضی وقت چیز میشه. مسئله کامپیوتر ساینس باید بسیار میتونی واضح چیز باشه. به خاطر اینترنت یا یه چیز دارم با خودم ده هم درس خواندم لیسانس خودم یا برش چیز میته پیسه چیز میته باید یه چیز کنیم. شما ریکوست کردیم در گروپ خونه فون باز تعقیب نکردیم چطور بود برسکار اسکالرشیپ چیز میکنه یا مقدار پیسه که یا تعیین کرده باشه او برش میته. کم نمیفهمی بچه در گروپ یک چند دفعه مسیج کردن که میریم گپ میزنیم که تشان مسیج میکنیم ایمیل میکنیم باز نمیفهم چی شد.
والله کسی تعقیب نکرد دیگه. مقدر یک گپ زده شد در مجلسه عمومی دیگه تعقیب نشده است.
درباره اساینمنت خود نمیفهمی اساینمنت ها یا دیدلاینش چی وقت است؟
تا هنوز اعلام نکرده دیگه. یک بار ختم شد نه 3 نوامبر بود. گفتن که دوباره چی میشه تمدید میشه، ولی تاریخ تمدیدش دیگه تا هنوز اعلام نشده.
درست است بیادر. تشکر.
فکر کنم درسات تمام است دیگه. موفق باشید.
درسات تمام است.
استاد څنګه وختي درس بند کا؟ تقریبا دا خو د یوې نیمې نه تر 3:30 بجو پورې د کلاس راځي. زمونږ انټرنیټ وای فای لږه خرابه شو نو چې زه بېرته آنلاین شوم کلاس یې ختم و.